Okay, let's start the class. In last week, we talked about the GAN. We also mentioned that actually, if you want to implement a GAN, there are lots of ways to do. The best way to implement the GAN so far is to use the spectral normalization. Many people abbreviate this to SN-GAN. SN means spectral normalization. Okay, although there is already GAN, it does not mean that GAN can be trained easily. GAN is still famous for being difficult to be trained. Why it is difficult to train a GAN? It is arised from the property of GAN. Let's think about discriminator and generator. What do they do in the training time? What discriminator does is to distinguish the real pictures and the generated ones. Which is the fake pictures? This is what discriminator do. And what generator does is to produce fake pictures that can successfully fool the discriminator. In fact, these two networks, the generator and discriminator, grow together and help each other along the way. If only one of them stopped the training for some reason. If one of them stopped the training for some reason, the other one will stop the training too. And will start to get worse. Then the training process of GAN fails. So, if you do not train a discriminator, that is still not well optimized. Which means that your discriminator can't tell the difference between the real and the generated picture. Then, for the generator, it loses its training target. Accordingly, the generator can no longer improve its performance. Once the generator can't improve anymore, discriminator will also stop there. Once generator can't improve anymore, it can't produce more realistic pictures. Then discriminator has no way to improve too. So, when you are training discriminator and generator, as long as one of them no longer improves, the other one will stop afterwards. However, you have trained lots of networks so far. Can you guarantee that the loss will get lower and lower with more training steps? You can't, right? When you train a network, chances are that you need to adjust the hyperparameter to get desirable performance. As for the case of discriminator and generator, the process of their interaction is automatically done. During training, we can't adjust the hyperparameter when we are still training discriminator. So what we can do is to parry that the loss of discriminator can get lower every step. Once it doesn't get lower, the whole training process is very likely to fail. And the process of discriminator and generator that reinforce each other might stop. So when we train a generator and a discriminator, they have to compete with each other with similar level of competence. If only any one of them gave up this game, the other person will not be able to continue. So the training process of GAN is still not an easy task. It is a very important and forward-looking technology. Some people might think that, please don't put a network that is extremely hard to train in the homework. However, I still think it is an important cut-edge technology. Accordingly, we should still give everyone a chance to access the most cut-edge technology. You can at least experience that. It is not easy to train a GAN. Of course, on the other hand, there are many people doing research in GAN. So you can find lots of programs or codes on the internet. From this point of view, it's not as difficult as you think. But training a GAN is still not an easy task. Well, you can find a lot of tips for GAN on the internet. However, are all of them useful? You never know. Here are some tips for training GAN. These are for your reference. Okay, the most challenging task for GAN, in fact, is to use GAN to generate texts. In other words, it is the most challenging. If you want to use GAN to generate a paragraph of texts. Why is it the most challenging to use GAN to generate a paragraph of text? We know that, if you want to generate a paragraph of text, then you might need a sequence-to-sequence model. You have a decoder. This decoder will generate a paragraph of text. Then the sequence-to-sequence model is our generator. This is the decoder when we talked about the transformer before. As for now, it plays the role of generator of the GAN. It is responsible for producing what we want it to produce. For example, a paragraph of text. Then you may wonder what is the difference between this and the original GAN trained on images? There may be no difference between them from the high-level perspective of algorithm. In the original process, when you train a discriminator that reads texts, the discriminator reads a text in and judges whether it is a real text or a fake text produced by the machine. The generator is trying to fool the discriminator by generating real-like texts. You need to adjust the parameter of your generator to make Discriminator. Think that the picture the generator produced is real. But what is the difficulty here? The difficulty here is that if you want to use gradient descent to train your decoder and to let the score which Discriminator output become higher, you will find that you can't do it. Why can't you do it? We know that gradient is related to how much an objective is affected when a specific parameter changes. Let's think about that. Suppose we change the parameters of decoder, which means that when the parameter of decoder has a little change, how much impact will the output of Discriminator in the end be influenced? If the parameter of decoder has a small change, the output distribution will also have a small change. Because this change of parameter is small, it will not influence the biggest token. What is the token? I know that the concept of token may be abstractive to you. If we go detail about the concept of token, we can think that a token is the basic unit in this sequence. And tokens are defined by human. Suppose we generate a Chinese sentence. We generate one character every time. We can think that a character is a token we defined. Suppose you are dealing with an English task. Every time you produce an English letter, then a letter is the token you defined. Suppose you produce an English word every time. Every English words are separated by blanks. In this case, a word is the token you defined. So the definition of token is decided by you. It depends on you to decide the basic unit of a sentence you generated. Okay, so today, when this distribution has only minor changes, the token with the highest score is still unchanged. As your distribution has only minor changes, the token with the highest score is the same. For Discriminator, the score which it outputs is exactly the same, so the output score will not change. Then, you will find that when the parameters of decoder change a little, the output of Discriminator is unchanged. Then, you have no way to calculate the gradient. You simply can't do gradient descent. Some students might say that. Is it because the max operator makes it impossible to do gradient descent? But we know that max pooling isn't component in the convolution neural network. How can it still do gradient descent? This question is left to you to think about. Why we can't do gradient descent here with max operators, but max pooling can do gradient descent. Okay, but even if we can't do gradient descent here, we do not need to afraid of this phenomenon. Do you remember what we talked about last week, that when we encountered the problem of not being able to use the gradient descent for training, we can consider it as a problem of reinforcement learning. So we can just use the methods in the reinforcement learning and solve this problem in a hard way. So you can indeed use the method in the reinforcement learning to train your generator. When you want to generate a sequence, you can use the method of reinforcement learning to train your generator. But what problems will happen to this? Reinforcement learning is famous for the difficulty during training. GAN is also famous for its training difficulty. When we combine GAN and reinforcement learning, boom, it doubled the difficulty of training. It will become very hard to train such model. So using GAN to generate a paragraph of text used to be considered as a big problem. So for a long time, no one can train a generator successfully. No one can use GAN to train a generator successfully. When training a generator to generate text, normally, you need to do pre-training first. Actually, we will talk about pre-training soon. If you don't know what pre-training is now, it doesn't matter. Anyway, you couldn't use normal methods in the past to let GAN generate a text sequence until there is a paper called Scratch GAN. Its title is just to show off to you that it can train language GAN from scratch. From scratch means that we do not pre-train the model first. So it can directly start from random initialized parameters to train its generator. Then, we let the generator generate text. How does it do it? The most important thing is to tune a lot of hyperparameters and plus a lot of tips. Then, you can imagine that this is Google's paper. After it tune a lot of hyperparameters, it add a lot of tips here. For example, this horizontal axis is their major. This is called fed. This one is used in text scenario. We won't talk about it today. It is not important. In short, the lower the value is, the better the performance is. At the beginning of the training, there must be a technology called seek-GAN step, which is necessary for training the model. Then, a big batch size is also necessary for training GAN. How large? Usually in thousands. You can't do this by yourself at home. Do regularization on the discriminator. Pre-train the embeddings. And change the algorithm of reinforcement learning. And you can get the scratch GAN. You can train GAN from scratch this way. And use it to generate sequences. Okay, today we only discuss parts of GAN. If you want to learn the full version, I leave a link here for your reference. Actually, generative models not only consist of GAN. There are more. For example, VAE. For example, flow-based model. I also list the links to the videos of those models here. For your reference, I want to emphasize that the videos provided do not mean you have to watch these videos to be able to learn the next lectures. There are so many things to learn in machine learning. So, if you don't have much time, the only thing you really need to attend to is what I said in class. The lecture is self-contained. It is consistent. As long as you attend every class, you should be able to understand the following lectures. In class, I will put some links to other videos. These are extra information for you. If you are really interested, you can conduct more in-depth research. So why don't we talk more about it? Because of the design of this class, the content of this course is designed to be practical. It is practice-oriented. Suppose you want to train a generator. You want the machine to produce something. You have many ways, like GAN, VAE, or flow-based model. Here we choose to teach you GAN. So, in the future, if someone asks you to train a generative model, you know how to train it. If you want to have an in-depth study, you can study VAE and flow-based model. Someone might ask, why choose GAN? Why not choose other models? The most intuitive and the most direct reason is GAN's performance is better. If you want to produce very good pictures, you need to use GAN. Usually, the results of VAE or flow-based model is of lower quality compared to GAN. You usually have to work hard, do a lot of parameter tuning, use a bunch of tips, only to get results similar to GAN in the end. So GAN usually has better results. Then you might say, GAN is harder to train. Or, GAN may be harder to train. Would VAE or flow be easier to train? Well, if you have experience in VAE or flow, they are not easier to train, to be honest. You might think, GAN looks mysterious. Judging by its formula, there is a discriminator and a generator. And they have to interact. While flow-based model and VAE are more like training a general model directly. They have a very clear objective. But when you actually start training, you'll realize they are not so easy to be successfully trained. There are many terms in their objective. There are many terms in their loss. You have to balance everything to have good results. But it's very difficult to strike a balance between them. I think training them is at least not easier than training GAN. So we choose GAN here as the generative model to introduce in our class. As for other models, you can, if you are interested, look into them by yourself. Okay, so far, maybe some classmates would wonder, why do we need to propose some new ways to be generative if our goal is to input a Gaussian random variable, that is, input a Gaussian and sample vectors from these Gaussian random variables and turn it into a picture? Can't we use supervised learning to do it? How? I have a bunch of pictures. I take out these pictures and assign every picture a vector, which is sampled from the Gaussian distribution. Next, use supervised learning to train them. And it's over. Understand? You train a network. In this network, you already said this picture is assigned this vector. This picture is assigned this vector. Train a network. Input a vector, and the output is its corresponding picture. Take the corresponding picture as your training target. Train it and it's over. Can we do this? Yes. There are such generative models. The difficulty is that, if you put a random vector here, the results of training will be bad. You may not train your model this way. So, what to do? You need some special methods to arrange these vectors. As for what kind of special methods, I will also put the link of 2 reference papers here. Everyone found out that this is not a very old paper. For example, the paper, Gradient Original Network, is published last year, last July 20th. These are relatively new papers and methods. I will put the link here for your reference. Okay, what we are going to talk about is the evaluation of GAN. How to judge whether the generator we have trained is good or not. It is not easy to evaluate the quality of a generator. The most intuitive way is finding someone to check. If you want to know that the pictures generated by the generator look like an animated character, you can find someone to look at. Maybe it's over. Actually, for a long time, especially when people were just starting to study techniques like generative models, there is no good measurement. At that time, the quality of the generator was evaluated by human eyes. And then the authors claimed how powerful their work was by just putting a few pictures at the end of the paper and said, "Hey, look at these pictures. I think it is better than the results of the current literature. Awesome. This should be state of the art." It's over. The GAN-related paper in the early years has no numbers. There is no measurement in the whole paper. No accuracy. It just put a few pictures to tell you this should be better than previous articles. It's over. You know this is not acceptable. There are many problems. If we fully judged the results by human eyes, for example, not objective, or unstable, and so on, is there a more objective and automatic method to measure the quality of a generator? For some specific tasks, there are ways to design such methods. For example, in Homework 6, we just want everyone to generate the avatars of the two-dimensional characters. There is an evaluation standard in the homework. We run a face detection system for animated characters, and then look at the number of detected faces of animated characters in the pictures you provided. If you provide 1,000 pictures with 900 detected faces, and the other one provides 1,000 pictures with 300 detected faces, then the generator of the results with 900 detected faces is relatively good. But this is the design for Homework 6. What if it's a normal case? Let's not be limited to our homework. In the normal cases, I train a generator, which doesn't necessarily generate animated characters, because it generates other things. It can generate cats, or generate dogs, or generate zebras, and so on. How do we know whether it is good? There is a way. Run an image classification system. Input the pictures generated by your GAN to the image classification system. See the result. The input of the image classification system is a picture, and we called it Y. What about the output? The output is a probability distribution, which is called probability of C given Y. Probability of C given Y is a probability distribution. The more concentrated this probability distribution is, the better the generated picture is. Although we don't know what is inside the generated pictures. We don't know if it is a cat or a dog, or a zebra. We don't know what it is. But if we input it to an image classification system, and the result of its outputs, as well as the distribution, is very concentrated, it means that the image classification system is pretty sure what it saw. It's pretty sure it saw the dog. It's pretty sure it saw a zebra. It means that the picture you generated may be close to the real picture. That's why the image classification system can recognize it. If the generated picture is neither fish nor fowl, or I don't even know what animal it is, the image classification system will be very confused. And thereby the probability distribution will be very flat, very evenly distributed. If it is evenly distributed, it means your GAN and the generated pictures may be strange. So the image classification system can't recognize it. Okay, so this is based on the image classification system to judge the quality of the generated pictures. This is a possible approach. But this approach is not enough. What's the problem with this approach? With this approach, the evaluation method will be fooled by a method called mode collapse. What is mode collapse? Mode collapse means, when you are training GAN, sometimes you encounter a special situation. Suppose these blue stars are the distribution of the real data. The red star is your GAN, your generative model's distribution. You will find that the pictures generative model outputs are just those few pictures. They're just those pictures. If you take out one picture, you may think that it does a good job. But if letting it produce a few more, it will show the bad things. You'll discover that it is bluffing. It turns out that only those pictures will be generated. The following is an example of mode collapse. Last week we said that I trained a generator that would produce the two-dimensional character When training to the end, I found that it became such a situation. This face was getting more and more. And it also had different hair colors. This hair color was more reddish. This hair color was more yellow. It's getting more and more. In the end, it's all this face. This is the phenomenon called mode collapse. Why does mode collapse happen? Intuitively, it's easy to understand. You can think of it as a blind spot of a discriminator. When the generator learns to generate this kind of picture, it finds that it can always fool the discriminator with it. The discriminator can't tell whether the picture like this is fake. This is a blind spot of the discriminator. The generator hits this blind spot, and mode collapse occurs. How to avoid mode collapse? I think there is no good enough answers yet. For example, last week we show the results of GAN. It will produce the result of a tennis dog. It was done by Google. It exhaustively tuned the parameters. But even it did that. It found that, eventually, it still had no way to really avoid mode collapse. In the end, GAN still has mode collapse. How does the paper on GAN solve this problem? It's actually really easy. When the model is training generator, I will save the training point along the way. Before mode collapse, I stop training. I just train to mode collapse, and take out the previous model and use it. Then it's finished. So even if it's Google's exhaustive search of parameters, there is still no way to completely solve the problem with mode collapse. For the problem of mode collapse, at least you know this problem exists. You can see that this situation is possible. When your generator always generates this face, you won't say that your generator is a good generator. You know that something happened, so that your generator is not very good. But there is another problem that is harder to detect. It's still a bit like mode collapse. It's called mode dropping. Mode dropping means that your real data distribution may look like this, but your generated data is only a part of the real data. If you just look at the generated data, you might think it's pretty good. And for the distribution, its diversity is enough. But you don't know for the real data. The diversity of the real data may actually be bigger. Let me give you an example. Okay, here is a real example. There is a student that trains the GAN to generate a human face. At a certain iteration, its generator generates these faces. You would think that there's no problem, and the diversity of faces is enough. There are men and women, looking left and looking right. It has all kinds of faces. Okay, this is the generator at the T iteration. You don't think there's a problem with its diversity. But if you look at the next iteration, the picture generated by the generator looks like this. Do you find the problem? There is a problem with its skin tone. So before, there is no problem with men or women. But its skin tone is pale. The skin tone here is yellowish. If you don't handle it well, people will think there is racial discrimination in your generator. So the problem of mode dropping is actually not easy to detect. In fact, today, these very good GANs, such as GAN, Progress GAN, Progress GAN, even these good GANs can generate very real faces. But is there any problem with mode dropping? Yes. If you see many faces generated by GAN, you will find that, although they're very real, but it always seems to have only a few faces. It has a unique feature. After you see many samples, you will feel that these faces seem to be generated. So maybe today, the problem of mode dropping is still not fundamentally solved. We will need to measure whether the images produced by the generator have enough diversity. How do we do that? In the past, there is a method based on image classification. Suppose you have 1,000 pictures produced by the generator. Just throw them into some image classification system and see which classes they are classified into. Thus, every picture gives us a distribution. Take the average over all distributions and observe how the final distribution looks like. If the average distribution is compact, it means that the diversity is not enough. If all the pictures you threw in are classified as class 2 by your classification machine, this means that all the pictures probably look almost the same, which also means that the diversity is not enough. On the other hand, if the distributions of the generated pictures thrown into the image classifier are very different, then the pictures should not be classified into the same category, and the average distribution should be relatively flat. What does this mean? This means that the diversity is probably enough. But if you think carefully, if we use an image classifier to evaluate the generator's diversity, then diversity and quality seem to be conflicting with each other. Previously, when we were talking about quality, I said, the more concentrated, the higher the quality. But to achieve greater diversity, the distribution should be flat. The flatter the distribution is, the greater the diversity will be. The answer to this contradiction is that quality and diversity are evaluated with respect to different things. Quality is evaluated on pictures one by one. If the quality is good, the distribution obtained by throwing one picture into the machine should be concentrated. But the diversity is evaluated on a set of pictures. If the average of the image classifier's distributions is flat, then the diversity is good. If the average is relatively flat, sorry, there are two averages here, flat and average are similar in Chinese. Hopefully you know what I mean. Anyway, the flatter the average is, the greater the diversity will be. There was a criterion that was used very often in the past, called Inception Score. Its abbreviation is IS. The Inception Score, as its name suggests, is calculated with the aid of a special type of CNN called the Inception network. How is it actually calculated? The process is simple. Calculate the quality with the Inception network. If the quality is high and the diversity is large, then the Inception Score will be greater. But we are not going to use Inception Score in our homework. Why not? Think carefully. If you throw the anime characters produced by yourself into the Inception net, all the outputs might be faces. Your generator may have achieved a big diversity by producing different hair colors or different eye colors. But for the Inception network, all of them are simply faces. Therefore, the diversity under this criterion may be small. So Inception Score may not be applicable to our homework. In our homework, we used a different evaluation measure. Frechet Inception Distance. The abbreviation of this measure is FID. What is this? First, throw the images into the Inception net. If you let the image pass through the Inception net completely, then you will receive a classification output, human faces, which is obviously unable to distinguish between pictures. So we should not use that result. Instead, we are going to make use of the output of the hidden layer before it enters the softmax layer. We will use the output vector, which might be a several thousand dimensional vector, to represent an image. Because we picked out the output vector from the hidden layer, but not the classification result. Vectors that are going to be classified as faces can still differ slightly. The vectors might contain informations such as hairstyle, skin color, and so on. That's why we will not use the final category of the pictures. Every image is now represented by a vector, which is the hidden layer's output. On this page, the red dots are the vectors obtained by giving real pictures to the Inception network. In reality, the vector's dimensions are very high. For simplicity, let's assume that they can be put on a two-dimensional plane. What about the blue dots? The blue dot represents the pictures produced by your own generator. Throw them into the Inception network. Take out the vector before the softmax layer and draw them on the plane. Suppose it looks like this. Now let's assume that both the distributions of real pictures and generated pictures are Gaussian distributions. Then, we calculate the Frechet distance between the two Gaussian distributions. That's it. As for what Frechet distance is, you can read it up yourself if you're interested. The judging system for the homework will handle that for you anyway. Alright. Since it is a distance, we want the value for it to be as small as possible. The smaller the distance, the better the quality of the generated image, since that implies the two sets of images are close to each other. You might still have a lot of questions in your mind right now. For example, you might question if it's fine to treat it as a Gaussian distribution when it doesn't quite seem like one. Well, yes, this method does indeed have its flaws. Or, you might wonder, if we want to get the distribution of your network accurately, Wouldn't we need to generate a lot of samples to achieve that? However, that does require quite a bit of computation. It's also an inevitable problem when doing FID. That's the reason why we won't only focus on FID and nothing else. If we only focus on FID, the results would be quite bizarre. The reason is that we assumed the distribution of the output to be a Gaussian distribution, which in reality it was not. Is it weird to assume it to be a Gaussian distribution? Yes, it is a bit weird. That's why we use FID alongside the number of anime avatars detected as the indicators. When we use these two indicators at the same time, we can achieve a more reasonable and a more precise result. So, FID is one of the more commonly used measurement. There is a paper called "Are GANs Created Equal? A Large-Scale Study." It is a paper published by Google, in which are the implementations of a variety of different GANs. Here is a list of the various GANs they have implemented. There are all kinds of GANs. Each GAN has a slightly different objective during training, as well as a different loss. I won't go into the details about different kinds of GANs. Next, they tested all the GANs using different random seeds every time. After running it many times, here's the result. The following graph represents the results they got on 4 different datasets. The horizontal axis represents different GANs. As for the value on the vertical axis, the smaller it is, the better it is. Wait, it is supposed to be FID. I think I wrote it into FIT. I'm sorry, this is supposed to be FID, not FIT. This is the FID score. And the smaller, the better. You can see that every item here is a distribution instead of a value. Why is that? Since they ran the tests with random seeds, the results would be a bit different every time. That's why the collection of results is a distribution instead of a value. Among the methods used, all are using GANs except one. One of the methods uses a VAE. We can see that the method that uses VAE is more stable when compared to the methods that used GANs. Different random seeds used in training VAE didn't make much differences. The GAN method, on the contrary, got affected seriously by different random seeds. You can clearly see that the difference in performance between VAE and GAN is substantial. While GAN can produce far better results than VAE, we can see that different GANs seem to perform similarly. That's why the name of this paper is "Are GANs Created Equal?" The various GANs do seem to perform similarly. This kind of conclusion makes for a clickbait that claims all GANs are almost the same, and any research related to GANs is just a waste of time. Well, that's not quite the case in reality. If you read that paper carefully, you would find out that every GAN listed there used the same network architecture. In their experiments, all they did was tune the learning rate and random seed by brute force. The network architecture is still the same one. So, we still don't know if some network architectures actually favor certain kinds of GAN, or if certain kinds of GAN perform more stably using different network architectures. For example, if we look at the original paper that proposed WGAN, it claimed that its network architecture could be designed without much thoughts. One could design a 100-layer generator, which is totally unnecessary, and the model was still able to be trained successfully. So, maybe WGAN performs more stably when using a different network architecture. Perhaps different random seeds won't affect the stability too much. We have no idea, and this paper doesn't give a clear answer neither. Okay, in fact, those measures we just mentioned didn't completely solve the evaluation problem of GANs. What else is left? Imagine this. Assume this is the real data. For some unknown reasons, you trained a generator that generates images exactly like the ones in the real data. So, if you don't know what the real data looks like, and you just look at the output of this generator, you will feel great. It did a great job. The calculated FID must be very small. But, the question is this what we want? If the pictures it generates are the same as those training data in the database, why don't we directly sample images from the training data? The training data is in your hands. Why do we need to train a generator? Training generator is actually because we want it to generate new pictures in the dataset. Those faces are not in the training data. If there is an exact same face in the training data, we may directly use the face in the training data, and there is no need to use GAN. So, sometimes your GAN generates very good results. Maybe, in your homework, FID is very low. The face recognition system also gives you a high score. But it may not be a good GAN. The problem like this is not measurable in our homework. But, it is a problem. How do we solve it? You may say that we compare the pictures generated by our generator and the real data by similarity to see if it's the same. If many pictures are the same, it means that generator just memorizes the training data. It's not very powerful. But, if I ask another question that, assuming what your generator learned is left-right reversing all the pictures in the training data, then, it also doesn't do anything at all. Assuming what it learned is left-right flipping on all the pictures in the training data, then, you will feel that, well, it looks great. But it doesn't do anything at all. Hence, merely using similarity as the comparing measure is not enough. So, the evaluation of GAN is very difficult. Even how to evaluate the performance of generator is open research topic. If you are interested, here is a related article. There are more than 20 kinds of generators evaluation methods. For you information. Okay, what's next? We are going to talk about conditional generation. Maybe, after we talk about the conditional generation, we could take a break. Then, the next section is for the Tush to talk a little bit about the homework on GAN. Okay, what is conditional generation? So far, for the generator we have talked about, its input is just a random distribution. Then, it may not be very useful. What we want to advance further now is to manipulate the output of generator. We give it a condition, x, and let it generate y, based on x and z. For such conditional generation, what kinds of applications are there? For example, you can generate pictures from texts. If you want to generate pictures from texts, it is actually a supervised learning problem. You need some labeled data. You need to collect some pictures. You need to collect some human faces. Then, these human faces must have text descriptions to tell us that this one is red eyes, this is black hair, this is yellow hair, this one is dark circle, and so on. It could tell us like this. We need this kinds of labeled data like this to train this conditional generation. So, in tasks like text to image, our x is a paragraph of text. Then, you might ask that, how do we input a paragraph of text to generator? You should ask this question to yourself. You can do whatever you want. We used RNN to read it through to get a vector. Then we threw it to generator. Maybe, today, you can throw it to the encoder of this transformer to average these output vectors of the encoder, and then you could throw it into the generator. Anyway, you can use whatever methods you want, as long as the generator can read a paragraph of text. Okay. Then, you expect that you input red eyes. And then, the machine can draw a character with red eyes. But, the characters drawn are different every time. What kind of character it drawn depends on what kind of Z you sampled. If you sampled a different Z, the drawn characters would be different and have the same red eyes. This is what text to image wants to do. Can it really be possible to do something like this? Yes, it can. There was this homework in the past, but not in this semester. There was this kind of homework in the past. We just input a red hair. This is the result from the previous TAs. We input a red hair and green eyes. And then the result is like this. It generates all kinds of characters with red hair and green eyes. We input blue hair and red eyes. And then it generates all kinds of characters with blue hair and red eyes. You realize that sometimes, machine makes mistakes. For example, here is a different color pupil. Although we want to draw red eyes, it thinks that it would be acceptable by drawing a red eye and a blue eye. How do we make conditional GAN? Our current generator has two inputs. One is sampled from normal distribution, Z, and the other is x, which is a paragraph of text. Our generator will generate a picture, y. Then, we need a discriminator. If we follow what we have learned in the past, discriminator takes a picture y as input and output a value. This value represents how much the input picture looks like a real picture. It is a real picture, or generated by a machine. How to train this discriminator? If you see a real picture, just output 1. If you see a generated picture, just output 0. You can train discriminator, and then train discriminator and generator repeatedly. Maybe you could successfully train a generator. But in this way, it couldn't really solve the problem of conditional GAN. Why? Because if we only train discriminator, and this discriminator only takes y as input, what generator will learn is how to generate a very clear picture that can fool the discriminator. It will produce clear pictures, but the picture isn't correlated to the input. Because for generator, it only needs to generate clear pictures. Then it can fool discriminator. Why does it need to care about the input text description? Your discriminator doesn't consider the input text, so it doesn't need to care about the input descriptions. No matter what text you enter, just ignore this X. Anyway, it just generate a picture, and it's over if it can fool discriminator. But this is obviously not what we want. So in conditional GAN, you have to make a different design. Your discriminator doesn't just input pictures. It also has to take input condition X. For your discriminator, it takes y as input, as well as x as input, and then generate a value. Then this value cannot be assessed by only check if y is good or not. If it only generate a good picture, then it isn't good enough. Discriminator still won't give high scores. If it only generate a good picture. Under what circumstances will discriminator give high scores? Not only should the picture be better, but the picture must also correlate to the X, which is the input text description. The picture must correlate to the input description, and then discriminator will give high scores. How to train such a discriminator? You will need text and image paired data. So conditional GAN, in general, need this paired data. It needs labeled data, and paired data. With these paired data, then you can tell your discriminator. If you see these real paired data, just give it 1 point. If it sees red eyes, I don't know why it is look like this here. But it doesn't matter. Anyway, I didn't put anything special on my side. Just a less important pictures. Maybe for images with red eyes and the pictures generated by the machine. Discriminator will output 0 point. Then keep training. Then you can make conditional GAN. But in practice, it's not good enough. If we just use the positive samples and the negative samples to train such a discriminator, usually it is not enough that this situation is good. Simply telling discriminator that this is a good situation and this is a bad situation is not enough for yielding good results. You should also add a bad situation, meaning that it has generated a good picture, but the picture is not correlated to the text description. So a common solution is deliberately pair the text with wrong pictures to produce new data, and tell your discriminator, if you see this situation, you have to say it's bad. Using this kind of data, you could train the discriminator well. Then let generator and discriminator training repeatedly. You will get good results in the end. This is conditional GAN. So in the current example, it usually generates a picture given a text description. The applications of conditional GAN is not only generating a picture given an input text, but also generating a new picture given an input picture. There are also many applications about generating a picture given another picture. For example, give it a design plan of a house. Then let your generator directly generate the house. Give it a black and white picture, and let it paint with color. Give it a sketch map, and let it turn it into a reel. Give it a daytime picture, and make it generate the picture at night. Sometimes, for example, you will give it a foggy picture, and make it generate a picture without fog, by removing the fog. So, in addition to generating pictures given input texts, you can also input images to conditional GAN to generate images. The name of this kind of applications is called image translation. Someone also called it pix2pix. This pix is pixel. It's the abbreviation of pixel. So it's called pix2pix. Okay, how do you implement it? There is no difference from generating a picture given an input text. Now it's just generating images from images. Replace the text part with an image. Of course, in the same way. To make such a generator. To generate a picture. Input a picture to generate a picture. Of course, you can use the supervised learning. In the literature, you will find that if you use the method of supervised learning, you can't get very good results. Usually, the result of a generator that uses some pictures as the input and trained by supervised learning may look like this. This is the input of your generator. And this is the output of your generator. You will find that it is very vague. Why? Maybe it is because the same input may correspond to different output pictures. Just like the example we've mentioned at the beginning of this class. The elf may turn left or turn right at the same corner. As the result, they learn to turn left and turn right simultaneously. In the image-to-image case, it's the same. For a given picture, there are several different possible outputs. What generator learns is to average different outputs, which results in a vague picture. So at this moment, we need to use GAN to train. You need to add a discriminator. The input of the discriminator is a picture and a condition. Then it will output the result after checking whether the condition and the picture match or not. This is the output of GAN. From the paper in the upper right corner, you will find that if you use GAN only, there's a small problem. Though the pictures it produces are real, however, it is way too over-imaginative. It will generate something that the real pictures do not have. For example, this is a house. But there is nothing in the upper left corner. However, it adds something like a chimney or a window there. Empirically, if you want to have the best result, you should use GAN and supervised learning. At the same time, using them simultaneously can usually yield the best results. By simultaneously, I mean when you train a generator. On the one hand, it is going to fool the discriminator. And on the other hand, it wants to generate a picture, which is similar to the real pictures. It does both at the same time. This often produces the best results. Conditional GAN still has many applications. Here is an interesting application. Given in short audio as the input, and GAN will generate a corresponding picture. What does that mean? For example, listen to a dog barking, and hope GAN can output a dog. I just said that conditional GAN needs the label information. It needs paired information. The sound and the picture are paired in the data. Actually, it's not that difficult to collect them, because you can collect a lot of videos easily. There are both images and sound in the video. Then you know, this frame of image corresponds to this audio. This frame of picture is paired with this audio. The picture of this frame corresponds to this. After collecting them, you can train a conditional GAN. Listen. And let it imagine. What does it looks like? Okay, this is made by a student in our laboratory. This is a demo. Let machine listen to this audio clip. It sounds a bit like the sound of a broken TV. What does the machine think it heard? The machine felt that it heard a creak or a waterfall. We listen to another audio clip. The machine felt it heard a speedboat in the ocean. Yet I am a little worried that maybe the machine have not really learned the relationship between the sound and the picture. Maybe it merely saves the pictures that have been seen in the training data. So, I decided to turn up the volume. Listen and see how it turns out. So we turn up the volume. Be careful, it gets really loud next. Okay, then the voice gets louder and louder. You will find that there are more and more splashes in this stream. It becomes Nicaragua Falls from a creek. The same for the speedboat example. Just make the speedboat's voice louder. Listen and see what happens. When the sound is getting louder and louder, you will find that there are more and more splashes besides the speedboat. It seems that the speedboat is driving faster and faster. But I have to admit that there are specially selected results. Most of the time, the output of the generator is like this. It's incomprehensible. We give it a piano sound. Then it seems to want to draw a piano. but not very clear. We give it a barking sound. It seems that Generator wants to draw an animal, but it doesn't know what to draw. This is the result of sound to image. Recently, the most amazing application of conditional GAN is to make pictures alive. We know in Harry Potter, the portraits are live and they can talk. Samsung made a similar application with GAN. Given a picture, for example, the portrait of Mona Lisa, then you can make Mona Lisa speak. This is one of the applications of conditional GAN. I put the paper link here. Okay. We can take a break first. We'll be back in 10 minutes. After this, teaching assistants will announce homework 6.